now we get the second derivative test. Okay, first derivative test is our main way of talking about increasing and decreasing, which leads us to the discussion of mins and maxes. Second derivative test, we start talking about concavity more. So, I think I just summarized this. Here we go. Concavity tells us the direction of a curve, how it bends. Just like a direction, concavity of a curve can change too. These points are called inflection points. So when mins and maxes change, when increasing and decreasing change, it changes at a min or max. When concavity changes, it usually changes at an inflection point. So, okay, concavity exploration. Draw small tangent lines at the points along the curves below. What do you notice about the slopes of the tangent lines, or in other words, the derivatives, as you move from left to right at these points? So, small tangent line. So, like right here at this point, there would be a tangent line, something like that, right? And just small so they're not all overlapping. Right there, right there, right there, kind of, right? What do you notice about the slopes of the tangent lines as we look at the first to the last? So the farthest left to the farthest right.
So negative to positive.
Okay. And not just negative to positive, but they are also along the way increasing, right? Okay, getting bigger because this one was negative, right? Then we have small positive, bigger positive, steeper slopes or even bigger positive, right? So the idea of what we have there is that my slopes are increasing. So that means f prime is increasing. When you find that f prime is increasing, that means that the graph is concave up. Okay. As you can already tell, in this particular graph, my tangent lines obviously lie below the graph of f. So anytime you have a concave up graph, your tangent line should be below the graph. Now, what about B?
Concave down.
Okay, so slope, slope. I am struggling to draw these. I don't know why. There's one. There's two, kind of. There's two, or there's three, there's four. I don't know. They're not the greatest, but as you look at these from left to right, what are my slopes doing?
Increasing, but then decreasing.
Well, technically, so here we have a positive slope, yes?
Mm-hmm.
Then we have a negative slope, so that's definitely decreasing, right? As we look at these slopes are getting steeper and steeper. As they get steeper and steeper in the negatives, they are getting smaller and smaller. So with that idea, the derivative here is decreasing. If the first derivative is decreasing, this means my graph is concave down. Notice here, tangent lines lie above the graph of f. Okay. Concavity definition. Not what we usually use to test for concavity, but concavity definition that we just showed. Let f be differentiable on an open interval. The graph of f is concave upward on the interval if the first derivative is increasing on the interval, and it's concave downward if the derivative is decreasing on the interval. Now, it's easier to check if a derivative is positive or negative than it is increasing or decreasing, unless, of course, you have a graph to look at every time. So what we will focus on probably more than anything here is the test for concavity, and that says, and I've talked about this previously, if the second derivative is greater than 0, so that's saying if the second derivative is positive, then the graph is concave up, and that's the graph of f. If that, I'm not going to be able to do this. Nope. Forget it. It's not happening. If the second derivative is less than 0 being negative, put that over there, then the graph is going to be concave down. Okay?
One down, 7 to go.
Wow.
At least there's a few quick ones, right?
Ooh.
So example 1. Given f of x, determine the intervals on which the graph is concave up or down. State the point of inflection. Explain how you know.
I just did this.
Just cause.
Well, the first derivative is x squared minus 1,
Guess what?
and the second is.
I already have it, so you don't need to say it. You somehow know you're not funny.
It's so hateful in here. It's so hateful. Okay, guys. So easiest thing to do here.
It's out of love, Mrs. Sargent.
Huh?
It's okay. It's out of love, Mrs. Sargent.
Uh-huh. Sorry, I was reading a note
One-sided love.
off to the side. Okay, I don't need that till later. So, first derivative is x squared minus 1. Second derivative is 2x. Okay. Set your derivative equal to 0. If 2x equals 0, then x equals 0. If it's a first derivative equal to 0, you're probably talking about a min or a max, an extrema, right?
Yep.
Because this is a second derivative equal to 0, what I'm going to say, POI, question mark? Point of inflection, question mark. Now, if it was me, I would just say IP. Okay, inflection point. But you usually see POI, point of inflection. Maybe that's because I just realized as I said it out loud how bad that sounded. But anyways, when I said IP.
Oh.
After I said it, I was like, maybe that's why they don't use IP. I don't know.
even think about
I don't.
I don't know. So, anyways, now, we don't just assume it's a point of inflection. We need to check. So we're going to do a sign chart, a number line. What number is going on this? 0. And keep in mind, this is the second derivative that we are testing here. Okay? To the left of 0,
-1.
plug in a number. When you plug it into the second derivative,
Negative.
it's going to be negative. What does negative mean in terms of a second derivative?
Down.
That means the original graph, f, is concave down. If we plug in a value to the right of 0, so 1, 2 times 1 is a positive. A positive second derivative means the actual graph, original graph is concave up. Okay? So what does that confirm about 0?
Inflection.
It is an inflection point. POI. And that POI, I mean, that's universal calculus, abbreviation there. Okay, now, officially, what were we supposed to do?
Explain how we know.
No, you're not.
Determine open intervals on which the graph is concave up, concave down, state the point of inflection, explain how you know. So, f of x is concave up on what?
0 to infinity.
Agreed?
Yep.
Why?
Since
Since concave is up.
Since second derivative, yes.
Since f double prime of x is
then 0.
greater than 0. Okay. F of x is concave down, or concave downward if you want to be fancy,
It's down.
on the interval
Negative infinity 0.
negative infinity to 0,
Man, just letting your sweat. You're claiming this.
because
F double prime of x is greater than 0.
Less than.
Dang it!
less than 0 because it was negative.
That makes me rage.
You sound like the basketball
Okay.
player.
It's not okay to be wrong.
F of x has a point of inflection at
X equals 0.
x equals 0
Since
Can you say since concave moves from up to down, or you have to say negative to positive?
since f double prime changes sign.
Alright.
you need to go yes, it's because concavity changes, but what's proving the concavity changes? And that's the sign change. So I have f double prime of x changes from negative to positive. I think you could do a generic changes sign because it wouldn't matter which way it changes. So talking about this,
Yeah.
it is. You just have to keep track of what you're doing. And I know it gets annoying writing all this. Do you have to write this on multiple choice? You don't. But on free response questions, are you expected to write this?
Yes.
You are. And so if I don't practice this here, come AP review time, you're going to be clueless. So I've got to do some practice along the way, right?
It's going positive so far.
Okay. So, example 2. I'm trying to look and see. Well, I'll come back to the screen here in a moment. So, graphs of derivatives. If you notice these equations, they should look a little familiar to you. The concavity, f double prime, and direction, f prime of the function f of x, is related to the slope of the derivative. So, what I want to do here, which way do I want to do this? There's always so much on this one. This one takes my brain a moment to look at this. So we're going to graph
It's a stretch, right?
the original problem.
Did we just talk about that?
That's a shrink.
Or shrink?
A shrink, yeah.
Put it around.
But I'm not graphing in terms of shrink there because there's also a minus x, which changes everything. And we're going to graph the first derivative. And we're going to talk about how these affect everything else. Okay? Now,
Right? No.
what's a parabola?
I feel like it's squared.
X squared minus 1?
The derivative.
Yeah, the derivative is.
Oh, I can
Huh.
graph that one.
Good job.
Okay?
I
Now,
thought you were talking about
You move it down one.
okay?
Yeah, x cubed is squared.
X cube's a squiggle. We'll talk about that squiggle here in a moment. This is a parabola move down 1, yes?
Yeah.
And so it's going to go through there. Where does it go through on the x-axis?
Negative 1 and 1.
And for what reason are you saying that?
Setting it equal to 0.
Okay. And so what I'm just going to go back here. We didn't talk about this up here, but we had our first derivative, yes?
Yes.
And that first derivative, if we would have set it equal to 0, and I did this up above there, then what? X squared equals 1 and x equals plus or minus 1. I also know just because, think about a parabola. What's the first set of dots in a regular parabola do?
Up one.
They go over 1 up 1, right? So you could also think that way. That's kind of what I was expecting you guys were thinking, to be honest. So I'm glad that you were thinking about zeros, because that's good. Now,
This just goes with what we talked about, like, what was the first unit, where if you have an x cubed, then its derivative is always x squared.
except now that's old news and, very basic.
So like the cubic graph is now.
Okay. Sorry, I'm trying to decide what I want to do here. So if we relate over here to, what do we have? We had 1, right? Sorry, I'm struggling with what is the best direction to take, you guys, so this all makes sense in the end. Okay, call you Mario now.
Oh,
Okay.
I dropped my gum on my paper.
And all Mario can do is laugh because he's done this several times. Okay, I only caught the aftermath of yours.
Yeah.
So,
I yawned and it just fell off.
okay. Now, with this in mind, right here, okay, we're going to work backwards. We're going to get over there here in a moment. Right here, what do you know at -1 and 1? Those are places where what?
It's going to be a min and a max, right?
That's where I'm trying to get you. The first derivative there equals 0, correct?
Wow.
So if those are places where the first derivative equals 0, based on the change of sign, those are going to be mins or maxes over on the original, yes? Now, between -1 and 1, what is the sign of my derivative?
Negative.
It is below the x-axis, so it is agreed that this is a negative interval, yes? To the left of -1 and to the right of 1, my first derivative is positive because it is above the x-axis, correct? Are you with me?
Yeah.
Okay. Now, what that says there, let's see. Also, what did we know from the previous problem? Concave down, concave up, and 0 was an inflection point. Now, I will say, notice right here, this is the graph of the first derivative, yes? So the slope, a minimum here, this is the slope, right? The second derivative, what do I want to say, of 0, well, yeah. The second derivative is going to be 0. So right there, that's your clue, second derivative equaling 0. That's like what we had up there. It shows as a minimum in the first derivative graph. Okay. Now, putting this all back together, we know underneath 1, there's going to be I didn't write it down over here. We didn't finish talking about it. If my graph goes from positive to negative, if my derivative goes from positive to negative, my graph goes from what? Increasing to decreasing. So what does that make this? What was that?
An inflection point? No.
No.
A min or a max.
A min or a max, but which one?
Decreasing is a max.
Min.
Oh, yeah.
Actually, what we probably need to do is go down and fill out this line, but what do we have over here?
Min.
A min, yes?
Yes, I did.
Here.
You had a 50-50 chance. You got
Okay.
it wrong. All right.
Let me, again, I'm going to make this graph the last thing we do, I think. Second derivative, we had a sign chart up above, yes?
Yes.
In that sign chart up above, what did we have?
0.
We had 0. We had,
Negative.
yeah.
I thought you were supposed to write.
I know, so did I. I thought we were going to write it.
Oh, no, in my brain, it's a sign chart. So this was negative and
Down.
concave down. To the right, it was
Positive. Contract.
positive and thus Concave up, yes?
Hi, thanks. I'm April.
Now, let's go to first derivative. We have this graph of first derivative, yes? What are my key points?
0, 1, negative 1, 0, 1, 0, 0.
Negative 1 and 1 on a sign chart.
Good job.
Because negative 1 and 1, or my sign changes from positive to negative, right? Or vice versa. To the left of negative 1, my graph was positive. Between them, it was negative. To the right, it was positive. Are you with me?
Yep.
Positive, negative, positive. Oh, you're trying to sketch the graph. aren't you?
Yeah, I'm just
Okay.
figuring it out.
Now, positive derivative means my original graph is going to be what?
Increase.
Increasing. A negative derivative means my graph will be
Decreasing.
decreasing and increasing.
So it just looks like that.
Oh, wait.
So I was right. Negative 1 being a max.
Oh, gosh darn it.
You
I don't-
literally said it from in.
Did I?
Yes.
Okay, now, oh, and we talked here, we already filled this out, that this is a max and a min, yes? Okay,
Seriously.
sorry. I'm not the best about teaching this, I guess, today.
It's okay. I understand it.
We know it's a cubic.
Yep.
Here's other information you can use. You know it's a cubic. It has a positive leading coefficient, which means a basic cubic that has a positive leading coefficient goes down to up, yes?
Yeah.
Now, mine has a min and a max in it, or a max and a min in it, though, yes? So if it has a max and a min, this guy is going to become more what?
A little warmer.
Like that?
You guys, and
Are you with me here?
Mhm.
Now, we've got to make that
Mountain balance.
happen on here.
Mhm.
Okay?
How do we know that the Y values, or do we?
We don't.
This is more.
We don't care.
We don't.
Okay,
Just about.
Okay? Now, what are we doing to the left of negative 1?
Increasing.
We are increasing. And at negative 1, there's going to be a max, yes?
Yes. Yes.
So I'm going to increase, increase, increase. There's my max. Arbitrary. No clue of what the Y value is, okay? Then, what do we do after negative 1?
0.
Decrease.
We are going to decrease. We're going to go down.
Positive 0.
We're going to have a minimum at
Negative.
1.
1. So we're going to end up having a minimum there.
We got across the board.
Officially, do we know that? I mean, I agree. I agree because if I plug in 0 here, it is. I'm trying to think if I officially know that.
I thought we did
It's
know
an
that
inflection
from what we
point.
did over here. From some kind of math that we did over here.
Yeah.
That math right there.
But that doesn't mean an inflection point doesn't have to cross at 0.
But it's 0.
It does here. So, okay. So a minimum under 1, and then we are increasing again. Yes?
Yeah.
Your graph looks something like that.
Yep.
Is that exact if you graph it on the calculator? Not necessarily, but that's the basic shape of it. Okay. Folks, that is typical thing to be able to, need to be able to explore and put the relations together. I'm not sure I did the best job about getting us there, but, you know.
We're pretty close.
We're good enough.
If you
And I guess-
zoom in super a lot, it'll look exactly like the one we have right up
Very,
there.
very possible. Where am I at on time? What do I have,
Like
about
4
4 minutes?
We can do 1
5
more
minutes.
page.
I don't know about a whole page, but
I was gonna say it's okay. Let's just. Put the
Okay. I've got 6 pages left.
No.
Okay.
I don't want to do this.
Let f be a function that is continuous on an open interval. Let c be a point in the interval. If the graph f has a tangent line at this point, then this point is a point of inflection of the graph of f if the concavity changes from up to down or down to up. So, if c is a point of inflection, then the graph either the second derivative equals 0 or the second derivative is undefined. Kind of like when we talked about first derivative issues. Most of the time, it's what makes the first derivative equal 0. Occasionally, there also is the undefined. Okay, those are valid points as well. Now, they don't give me directions what to do up there, do they? Do they?
Nope.
Okay, I think, so these are just the examples of each, is basically what you're looking at. So, the idea here, yeah. Okay. The idea that, are you seeing some of these, like in this case, would be your, I have it as P on mine, I think I was doing inflection point. Okay. And the idea here that to the left of this inflection point is concave up. To the right is concave down. And then if we look at the slope, I'm trying to put this all together in my head real quick, and I'm, gosh darn it. The tangent line through that inflection point, folks, is going to be something along the lines of, I can't get it. Something like that.
Yes.
Just go with it, okay? And the idea here that is an inflection point. My graph changes concavity there. But that first derivative is going to be increasing there. So f prime of p is greater than 0. Okay, it's a positive slope. The second derivative here would equal 0, and thus it is a point of inflection. The interesting part about this next one, what happens when you draw that tangent line? That tangent line ends up being 0 because it's horizontal. I keep drawing a little too high, but you guys get the idea. Looks something like that. Okay. Again, that's where our second derivative is going to equal 0. It's concave. It's a inflection point. You've got on the left this time it's concave down. On the right is concave up. This is going to be your other example, where now that line, I don't know if that graph's drawn exactly right, but you're going to end up with a vertical tangent line there. Okay? Mine didn't end up very vertical, but concave up to concave down, and there's an example where your second derivative is undefined or does not exist. Okay. We will talk more tomorrow. Now I know I have several that I wrote skip next to because I skipped them last year because of time.
You wanted to.